got a short video where we're going to work some examples which is related to the previous work we did on forces. Okay, so prepare some pencil, paper to work on. You also need your calculator and get ready. We're going to go through a few examples on force diagrams, vectors and scalars, mass, weight, and also something small on Hooke's law. As always with each question, pause the video and then try them out yourself first before checking out my explanations. To start off with, we'll do force diagrams. Okay, we'll do an example or two on force diagrams. So consider this lady riding on her bicycle. You have to draw a force diagram to indicate the forces that are acting on the lady and her bike. Up to you. Ready? Let's have a look at what you sketch. Now it's important here, remember, to have a good sketch and label the forces. Okay, so we've got our lady on the bike. Right, now since she is working on the bike, she's moving forward, so there we have a forward force. In the case of a car, it would be an engine force, but here we just say it's a forward force. Right, now, like everything on Earth, she has a weight just pulling her down, so she's got the arrow of the weight going down. We've also got the reaction with the ground, so where you've got the contact with the wheels, there you have reaction forces. And also we've got the frictional forces. We've got the friction with the ground, and we also have the air resistance, the drag. Right, so that is the complete force diagram for this particular situation. Next question is a paratrooper. You've got a soldier with a parachute, a paratrooper, alright, who's falling down from the sky. Draw the forces on this paratrooper. Hey. Ready now? Okay, so let's have a look. In this case, since the soldier is falling freely in air, basically we mentioned two particular forces. You've got the weight, which is obviously pulling the soldier and the parachute downwards, but we also have the air resistance. Right, the air resistance is very large. Note also the size of the arrow. The arrow is very large. Okay, because the air resistance is what is slowing down the soldier from falling to the ground at a fast speed. We'll be talking more about this later on. Okay, but keep in mind that the size of the arrows matters. Okay, so here we only have two forces, air resistance and weight. Okay, so next we'll look at something small which has to do with scalars and vectors. Remember that we had classified scalars and vectors. Remember also a scalar is a quantity, a physical quantity which only has a magnitude, whereas a vector is a physical quantity which has both magnitude and direction. So have a look at these, and as an exercise I just want you to classify each one of these physical quantities, what they are. Are they scalars or are they vectors? So you've got velocity, mass, acceleration, time, distance and weight. Okay, try it out. So we're ready? Okie dokie. So if I look first at the first column that we had velocity, mass and acceleration. Okay, now velocity, remember, was a bit different from speed, because velocity we needed to know the value and also the direction of where a car or whatever is going. So velocity is a vector. Mass, on the other hand, is something which depends purely on matter, on the particles, so direction does not affect it, and so mass is a scalar. Acceleration is something we mentioned, but we're going to talk about in a later video. Alright, acceleration is also a vector because it depends on the direction also. If we look at the second set, we have time, distance and weight. Time and distance are both scalars because direction does not come into it. When with respect to distance, we had also mentioned displacement, which is the vector part, okay? And weight, being a force, really depends on the direction, because forces, as we've seen also in the force diagrams, force we need a direction, okay? So when it comes to weight, weight is indeed a vector. Okay, so next we'll work something related to mass and weight. Remember that we had done this formula W equals mg, and remember also that mass was something which depended on the matter, on the particles, so it remained ever the same. It remained constant wherever we go. But weight was something which depends on the gravity, on the gravitational pull. Okay, so let's have a look at this example. We've got a man which has a mass of 80 kilograms. Alright, you have to find the weight of this man on Earth. We are taking the value of gravity, the value of g, to be 10 meters per second squared. Try it out. So, worked it out? Okay, let's see. So first of all, here we didn't have to do any conversions. Okay, so mass was in kilograms, so that is correct. W equals mg. Always remember to write the formula. We'll start from the formula. If it's a question of weight, W equals mg. We write the formula, write the numbers, work it out, get the answer, write the units. Okay, so W equals mg, mass was 80, g was given to be 10, so 80 times 10, and that will give us 800 newtons. So next, we've got a similar question. It is the same person with a mass of 80 kilograms, but this time we're going on the moon. So you need to find the weight of the person on the moon. Right now, the moon being smaller, the gravity, the acceleration due to gravity is much less than that one of Earth, which is 1.625 meters per second squared. Okay, try it out. Would it be nice on the moon? Okay. So, ready? So we start off again with the formula, W equals mg. Mass remains the same. Again, remember, mass is always constant, 80. But g this time, instead of 10, we have 1.625. So here we get 80 times 1.625, and we work it out, and it comes to 130 newtons. Alright, so note the weight on Earth was 800 because gravity was bigger on Earth, because Earth is much bigger than the moon, compared to the weight on the moon, which is of 130 newtons. And what about on Mars? Well, again, find the weight of this person, the same person, if this person was to go on Mars, where the gravity, the acceleration due to gravity, is of 3.75 meters per second squared. So it's more than the moon, but less than the one of the Earth. Try it out. Okay, so work that out now. W equals mg, once again, 80 times, in this case, 3.75. And that gives us a weight of 300 newtons. And what about in outer space? What is the weight of this man in outer space? What do you think? Think. What did we say about outer space? Well, remember that in outer space, when we refer to outer space, there is nothing around you. So there is nothing to cause the gravitational pull. So in other words, the value of gravity, the value of g in outer space is always taken to be 0. And in fact, that will result in a weight of 0 newtons. Not no weight, so be careful how you use the terms. It's a weight of 0 newtons. Okay? So through this, and this was the last one, through this set of examples, you should have refreshed how weight is something which changes depending on the value of the gravitational pull, as opposed to mass, which always remained the same, no matter where this particular person went. In the last part of this presentation, okay, we're going to just work something small which has to do with Hooke's law. So remember Hooke's law, okay? Remember Hooke's law stated that the extension of a spring is directly proportional to the stretching force, provided we don't exceed the elastic limit. Okay? So, as an example, to start off with, consider this. We have a spring which has an original length of 10 centimeters. When I place a mass of 100 grams, the length becomes 15 centimeters. So all I want you to do is reason out. There's nothing really to calculate, just reason it out. Reason out what is the value of the extension in this case, and also what is the value of the load. Okay, load is usually the force. Try it out. Okay, managed it. Let's have a look. So here we are asked to provide the load and the extension. Now the load, when we're talking about the load, we're talking about the weight. Okay, usually what weight do we have on our spring? So in this case, we are told that we had a mass of 100 grams. And what do we have to do with it? Well, we need to do the conversions. Okay, so first, 100 grams needs to be changed to kilograms, and that, remember, is division by 1000, so that gives us 0.1. And then we use the formula W equals mg, 0.1 times 10, because we are on Earth, and unless told otherwise, obviously we use the g of Earth, which is 10, okay? And 10 times 0.1 gives us 1 Newton. So the load here, we had a load of 1 Newton. We're also asked to find the extension. Now in the extension here, we just have to reason it out. So the original length was 10. When we put on the load, the length increased to 15. So if we simply subtract, that means that we have an extension of 5 centimeters in this particular case. So next question on Hooke's law. A spring extends by 10 millimeters when loaded with a force of 5 newtons. If it is loaded with a force of 15 newtons, by how much will it extend? Assume that Hooke's law is obeyed, and so the spring does not pass its elastic limit. Try it out. Manage something? Let's see. Now keep in mind that since Hooke's law is obeyed, okay, that means that the force and the extension are directly proportional. Directly proportional means that if one quantity doubles, the other quantity doubles also. If one halves, the other one halves. So they work hand in hand. So in this case, we can write down a simple statement like this. So 5 newtons is equal to 10 millimeters. 15 newtons equals how much? Okay, and you can either use the statement system or the simple proportion, because this is simple proportion, or you can even reason it out. I mean, here, from 5 newtons to 15 newtons, I am tripling the force. So since they are directly proportional, I would expect to have tripled the extension, and in fact the answer would be 30 millimeters. Okay, now this condition, that Hooke's law is obeyed and that the elastic limit is not exceeded, is often asked for in the exam. So make sure to remember it, and when necessary, quote it and write it down. Okay? Now in fact, Hooke's law, we can also represent it as a formula, and sometimes we do find this formula at ordinary level, at O level. Alright, at intermediate, advanced level they always use it, so it's used a lot. We can still reason out things from the numbers which are given, but sometimes the formula may come in handy. We didn't mention it in the other video of Hooke's law, I'm mentioning it now. F equals kx. Stretching force is equal to spring constant times the extension. Okay, as you can see over there. Now this is a very simple formula, F equals kx. What this particularly tells us is the value of the spring constant k. Now springs will stretch depending on how they are made. Different springs will stretch by different amounts and in a different way. And that is the spring constant. Not all springs will stretch the same way. Some springs are harder than others. Some springs are very soft and they will stretch very easily. And that difference is indicated through the value of the spring constant. Okay? So as a final example, how much force is needed to extend a spring which has a spring constant of 20 newtons per meter by a distance of 5 millimeters. Okay, so note that first of all the units of the spring constant is newton per meter. Okay, and also note that the extension here is given in millimeters, so be careful. I'll leave it in your hands. Try it out. You feel your head exploding? Nah. Yeah, it's pretty easy. It's just another formula we'll add to our list. So F equals Kx. Okay, so let's have a look. So F equals Kx. Very simple, don't need to stay changing around the formula. We were given the value of K as 20. Now the extension is in millimeters. And that is where you have to be a little careful, okay? To be able to use the formula here, everything must be in meters. So 5 division by 1000 gives us 0.005, and when I multiply that by 20 I get a force of 0.1 newtons. Okay? And that was the last one for today. So good job and well done for that. Okay? And in fact that's it for this video. We'll be working more and more examples on these topics throughout our work, so that we keep on consolidating the principles we're learning. However, it's important that you go through these questions more than once, so that you help yourself revise and strengthen your knowledge in the topics. Okay? So here we covered examples related to the topic of forces, and we touched on many different areas. Okay, some small areas here and there, starting off with force diagrams, and then we went on to vectors and scalars, mass and weight, and ultimately we also looked at some examples related to Hooke's law. So as always, I hope that you enjoyed this video, and thank you for watching.